Hello everyone, welcome back to a one-day game crash course by George Lee Cakes, myself. This is part 2 in the fundamental section of this video series. Now, picking up from last time, one thing you might have noticed is the fact that we're using several different applications to actually make stuff happen. And there's actually a rendering pipeline, or really a overall pipeline for creating content for a game. And to do that, we actually need about 5 stages. And this is the least number of stages you need. There's actually possibly a lot more, up to hundreds of different stages to get your final thing done. But this is sort of things distilled down to the smallest amount possible. 2 offline stages, which means they're not being done in real time. And then, of course, a CPU and then GPU stages, which we'd already looked at before. The first is the tool stage, which is considered offline, meaning it can take as much time as it needs to, but that's actually the generation of all the different assets and content you need. Then we have the asset conditioning stage, which is taking all of your tools or the assets you've created through using your tools and converting them over to some format that can actually work for you inside of your game engine, whatever that might be. Next up, we come to the real-time stages, and the first is the application stage, which is where your game or application is running. Then we have the geometry processing stage, where all of the different vertices and so forth are being processed by your GPU. And then finally, the rasterization, which is where the geometry is converted over to pixel values for you to work with. The first thing for us to understand is that things are set up to be in a pipeline format. And because of this, things not only get faster, but you also have things like bottlenecks that might interfere with how quickly things can get done. The great thing about a pipeline is the fact that you have multiple stages where all of your assets, all of your resources are working together to get something done. This allows you to have a tremendous speed increase and to work in parallel. Now, if you have a stage where people aren't working as hard as the rest of them, or if there's too much work to do in one stage, then you get stalled. And that is, everything before then has to be waited, and everyone after them also has to wait with nothing to do. So, what about that asset creation stage? Well, in our particular case, you're going to be creating meshes or other different objects, and you could be using any one of the bullet-pointed applications, although there are many more out there. In my case, I'll be looking at Maya. Really, the tool stage in terms of creating assets can be done directly in code, so you might not even be working with a mesh or with a 3D modeling program. But the general idea is that it provides you tools for things like modeling, lighting, animation, texturing, and rendering. But the problem is that when you're creating these models, most likely they're not created in a format that's compatible with your 3D engine. Typically they're in some format that is specific to the application you're working with. We need to extract this information and condense it and convert it over to something that can be used by your engine. A very popular file type is the FBX file type, which can be exported from Maya, 3D Studio Max, and many other platforms. We are going to be importing FBX files into our Unity project. Now, inside of the Unity program, you can also import Maya and 3D Studio Max projects. By using the FBX file format instead, you do not need to have access to these programs. Everything just works. So once again, please just export things out as FBX. Next up are 3 stages. I've already kind of gone into this before, but the idea is the application stage is all about things running on your CPU, collision detection, animation, physics, sound, and scripts. The geometry stage is where we take in all those vertices and we deal with them. It's about figuring out our local coordinates and then, of course, transforming them into world and then the view or the camera coordinates. And when all that's done, it's all about taking that information and turning it into pixel values which show up on our 2-dimensional screen. Now we're going to take a slight break here really quick and just talk about some of the history of the GPU, or the graphics processing unit. Graphics cards a while back ago actually did exist, but they were not meant for consumers. So unlike today, where everyone fights over the latest and greatest graphics card, back then most of us didn't even know they existed or didn't have any concept that you needed one. It was overkill really for a lot of the applications we were playing, such as Wolfenstein 3D. Everything for the most part was processed on the CPU. This did cause some problems though in a lot of applications where people didn't throttle the speeds properly and games would run at different rates based upon how fast the CPU was. Now, creating all those images on the screen was processed completely and entirely by the CPU. Now, this means it also shared resources with things like AI, physics, sound, and the input or the output. And this meant that if any one of these stages took a long time, that bottleneck appeared and things would slow down. The good thing about this was that you had tremendous freedom to create whatever you wanted to, so long as you knew how to. The limitation was the fact that the CPU itself could only do so much. Now, around the late 90s, Voodoo and NVIDIA provided their hardware acceleration and rasterization hardware systems, such as the Monster card or the 3DFX cards as you see below. This allowed us to create hardware through DirectX or OpenGL that pretty much made it so that you would use certain methods or functions or certain commands that would automatically and very quickly process things for you. This started off what we refer to affectionately as the fixed function pipeline, and that is you have an API, an application programming interface, which has a series of different commands or functions or methods or whatever you want to call them that allow you to basically turn things on, off, and set stuff up. You would then push all of your geometry, all your vertices and so forth, off into the hardware, and it would go through a series of stages such as lighting, assembly, and conversion over into pixel values. Finally, the hardware would do its job and push out a frame buffer or pixel image for you to show on your screen. The idea is by having separate hardware, you're no longer bogging down the CPU with handling all this stuff. Something else is dealing with it. The big problem here, though, is it's a fixed function pipeline, meaning you have very little ability to program it and change how it operates. Now, in the early 90s, OpenGL was a major force. Market changes, though, showed that DirectX around 1995 became the dominant market force, and a lot of things happened with DirectX, and a lot of people used it, especially since it was the dominant Windows platform to work with. Now, I won't go into comments, but Windows, or I should say Microsoft, in many ways on Windows, neutered the ability for OpenGL to work properly, even to this day. So that's kind of why DirectX succeeded so well. But anyway, Microsoft eventually tied DirectX to the releases in Windows, which also stifled its ability to update quickly. In the last 11 years, or, well, actually it's changed a bit. 11 is a little bit small. I'd say there's been at least 4 major releases of DirectX. Now, the great thing about the OpenGL system is the fact that they actually have an architectural review board that allows them to accelerate development and create new things. And really, OpenGL is doing a lot better than it was before, and it has a wonderful life on the Mac and Linux side of things. Now, around 2004, that fixed functionality pipeline just wasn't enough. People were getting tired of being completely restricted by it. So what ended up happening is we created, or I shouldn't say we, other more important and smart people created programmable vertex or fragment processors, which allowed people to program how things were dealt with on the vertex level and the pixel level as things were being handled and basically evaluated on the graphics processing unit. The idea here is you code up your own little scripts, you throw them out over there, and the hardware that's responsible for handling these segments would look at what you've done and handle them accordingly. This gave us more power, but also gave people a lot more requirements in terms of understanding how everything worked. It was not only up to you to throw all of your information at the graphics processing unit, but also program it properly. Now, over time, things have gotten a heck of a lot better. Now, most of you are probably going to say, computers got faster. But the reality is the programmable shaders for the vertex and the fragment shader have really advanced us more than anything else. But the Unreal Engine, if we look at it, and we see part 1 here with the first Unreal game, the jump from Unreal 1 to Unreal 2 wasn't that much. Yes, there are more vertices in here, but it's not a tremendous quality increase. If we go from 2 to 3, though, you'll notice a crazy amount of detail, and this is partly due to the programmable pipeline available. Now, we're just going to talk about a few more things real quick before we finish up. We're just going to touch briefly a little bit more on things like the application stage. Now, the application stage might need to do things such as determine whether or not something's visible on the screen. It might need to figure out which geometry should actually be sent to the GPU. The idea here is that you don't want to render everything. If you try to show everything in the world, well, basically, it would slow down and your computer would probably crash. So instead, we only render the things that are important. And of course, things like controlling shader parameters, telling the program how to execute and what it should do. And of course, that leads us right into the geometry stage, where we have things like transforming the model, which we've already talked about in terms of local world and camera-based coordinates. We have our vertex shader, our projection, our clipping. Basically, projection means projecting it onto a box into some sort of a format that's easy to work with. Clipping means cutting anything off that isn't within that box. And finally, screen mapping is mapping it to, well, our screen. The names kind of make sense, don't they? Next up, we have the rasterization stage. Now, parts of this we can't actually interfere with, such as the triangle setup and traversal. This is where we go over all the triangles in our scene and convert them over into fragments or pixel objects. Our pixel shader or fragment shader handles each of those pixel values. And then finally is our triangle setup and traversal. Now, there's a lot of kind of shaders out there, and there's only going to be two that we even care about for the moment, and that's the vertex shader and the pixel shader. But I wanted to make sure you understand that there's a lot more happening here than what I'm showing you. The vertex shader responsible for those vertices, those three-dimensional points. We have things such as the tessellation shader, which is where we want to increase the amount of detail on an object through the GPU programmably so that it looks more authentic or realistic. And there's also the geometry shader for the creation and destruction of objects. Then we have our pixel shader, which is all about drawing to the screen. And then we also have a compute shader because these GPUs are so tremendously powerful. That is, they can create so much data so quickly using its parallel architecture that many times we don't want to make an image out of these things. We instead want to be able to compute or work on a mathematical problem or some sort of problem that we have in academia. And that's why we have compute shaders to do that sort of thing. Now, I was going to show this animation of a T-Rex, but this is pretty old at this point. I think I made this when I was a grad student. But the idea is that how animation works is we don't want to mess with all the different vertices of an object. We instead create a rig which has bones inside of them or things that are bone-like, and they influence the vertices around them. And then we create this rig of different controllers, and as we move these different elements, all the different parts of that move around with us. So for instance, if we bring Maya up over here, here's a more recent rig that I had created in about a day for a horror game. And this is our flesh monster. And if I hit the play button, what ends up happening is we have this thing called a T pose, which is its basic pose that it stays in. And eventually we go to a bunch of different animations, such as idle, which is where he's just kind of casually breathing at us, waiting to do something. And then from there, we have another idle animation where he's looking to the left and to the right. Once again, doesn't really have anything to do. He's just going to stand there. But the idea is that the player, for some reason, has found this character. There's I don't know what that was, a bite. Then we have a lunge. We're going to have some walking animations and so forth, and a few other ones before we're actually done. There we go. We have like a scream up. We have a lean across the corner from one direction, and then a lean in the other direction, and several more animations. And that's generally what we would have to create this particular object in our game. And then we would export this thing out as an FBX with its animations and bring them into Unity, which we'll be looking at very soon. And of course, once that's brought in, we need to start adding things like AI to our assets. In this particular case, we're looking at an implementation that I created in WorldViz Wizard of behaviors, where the green guy is constantly moving towards the yellow one, which randomly changes as the game progresses. And everyone else, all the red ones, are continually trying to flock away from this green guy who's kind of like a predator within all of this. Now, the green guy is kind of floating and skating around because I made it so that the physics engine's more like he's on ice. But you get a really good sense of him trying to continually correct his direction and run towards whatever object is there. Now, that being said, that's pretty much it for the fundamentals. In the next video, we're going to do a math review covering things like standard vector topics, and we're going to get a look at how we can use math to better create our games. Thanks everyone who's watching the series. Remember, give me a like if you enjoyed it, give me a dislike if you didn't, and also comment as to ways I can make it better, and remember to subscribe. Thank you all. I'll see you next time. Have a great night.